All right, so in this module, we will be talking about inference rules. So if you remember, so far we've been talking about syntax and semantics, and now we would like to talk about how we can play around with formulas and manipulate them and apply inference rules on them. I want to talk about this diagram a little bit more for a second before jumping into inference rules. So let me go back to my whiteboard here. So basically, what I've been drawing here is we live in the syntax land and formulas live in the syntax land. So I'm going to draw them like this. So maybe I have formula F1, formula F2, through maybe formula Fn. Okay. And then in the semantics land, I give meanings to these formulas, right? So each formula has a corresponding set of models to it. So each one of these formulas will correspond to something that I'm calling models of F1. F2 might have another set of models of F2, and so on. And you might have a bunch of other ones. So let's say that I only have like 3 of these. Actually, let me make this F3 to make this simpler. So let's say I have F3, and F3 has another set of models corresponding to it, models of F3. Okay. And this part defines our knowledge base, right? So we talked about knowledge base being a set of formulas. And the shaded area corresponds to models of knowledge base. Okay, so this is models of our knowledge base. Okay, so this is what we have talked about so far. So now we want to talk about what inference rules really do. So if you have a set of knowledge in your knowledge base, this set of formulas in your knowledge base, the idea of inference rules is could you basically apply a set of syntactic rules on them, and based on those rules, I'm going to call them inference rules, infer something, a new formula here. So from the formulas F1 through F3 that you have, could you infer a new formula, a new G, that is just based on the formulas that you have and based on like symbolically manipulating them? And the question is, could you make sure that that G that you're inferring actually has a models that is a superset of, so this is models of G, is a superset of models of KB, because ideally you want to be able to infer something that just directly comes from the formulas that you have. So ideally you would want to be in a situation when models of G is going to be a subset of models of KB. And what does that mean? That means KB entails G, right? So could you have a set of inference rules that end up giving you a G, and then you end up in a situation where models of G is going to be a subset of models of KB? So could we come up with those set of inference rules and those set of Gs? So that is the idea of inference rules and what we're going to be talking about today in this lecture. Okay. All right, and that's basically what this diagram shows. So we have a set of formulas, each one of them correspond to a set of models. At the end of the day, I want to apply a set of inference rules on these formulas, and I want to be able to come up with models that is a superset of models of my knowledge base. Right? Would I be able to do that? All right, so let's talk about that. So let me give you an example. What do I mean by that? So let's say that I know it is raining. So in my knowledge base, I have that it is raining. And then I have that if it is raining, then it is wet. So rain implies wet. If I tell you that it is raining, and if it rains, that implies wet, what can you tell me from that, just from that knowledge? From that knowledge, you should be able to infer that, well, therefore it is wet, right? It's raining, and raining implies wet, so it's got to be wet. Okay, so that is the idea of inference rule. Could we like try to have a rule that tries to basically infer wet here? Okay, just based on the formulas. So in general, in inference rules, we have a set of premises, we have a set of formulas like rain, and rain implies wet. And based on that, we want to come up with a conclusion. In this case, for example, that conclusion is that it is wet. And that defines, like, in general, like inference rules. There's a specific type of inference rule that we are going to talk about. It's a pretty simple one, and it's called modus ponens. Okay, so modus ponens is a very simple inference rule. And what it says is that for any prepositional symbol P and Q if in my premises, in my knowledge base, I have P and P implies Q, that allows me to conclude Q, kind of like this example that we saw here. And you should think of inference rules as very like syntactic symbolic views of the world. So I basically just like look at my knowledge base. If I find anything that matches form P and anything that matches form P implies Q, from that I should be able to infer Q. Okay. Let me put this here in the set of my definition. So now we are at inference rules, and we are going to be talking about modus ponens. So modus ponens is an inference rule. It tells us if we have P and P implies Q, we can infer Q based on that. Okay. All right. So in general, inference rules, we can write them in this way. We have a set of formulas, F1 through Fk, and following an inference rule allows us to conclude G about it. And it depends on what inference rule we are using. Modus ponens is an example that we have just seen. And again, these rules are applied directly on syntax, and they do not care about semantics. They don't care about what raining means or what wet and raining and the meaning between them actually means, right? They're just applied on the syntax, on the formulas. And that's kind of the power of logic, right? Like we talked about these formulas as a compact way of representing much larger meanings, like exponential meanings a lot of times. And now on these very compact formulas, we can apply syntactic rules, we can apply inference rules, and based on them, we can infer new formulas and that have new meanings, basically. Okay, so if I want to think about what an inference algorithm does, kind of like a meta algorithm, an inference algorithm here does something of this form. So we have an input. That input is going to be a set of inference rules. We've talked about modus ponens as an example, but in general, I would have other inference rules. And what I'd like to do is I'd like to repeat this loop until there are no more changes applied to my knowledge base. And what do? I just choose a subset of my formulas from my knowledge base. And if I can match my inference rule and infer a new formula G, I will add G back to the knowledge base. And I keep doing this until there's no more Gs, no more new formulas to be added to my knowledge base. Okay, so that is what an inference algorithm does. And one other definition here is this idea of derivation and proving. So what we say is that a knowledge base proves or derives a formula F, even only if F eventually gets added to knowledge base. Okay. So going back to let's say our definitions. So now we have a definition of derivation or proving. And we're going to use, so we're going to say a knowledge base derives F, and we're going to represent that by this one line kind of symbol. So going back here, we're going to basically, if I have F1 through F3 in my knowledge base, if my knowledge base, if I apply inference rules and get a new G, I would say my knowledge base is deriving or proving G. And so on the semantic land, then I have this idea of entailment, which might be different from what we have in the syntactic land, which is this idea of inferring or proving or deriving. So, okay. All right. So we'll talk about the relationship between these two in a few slides, but let me just go back to talking about derivation a little bit more. Okay, so that is derivation, that is proving. So let's look at an example. Let's say that I have a knowledge base, and in my knowledge base, I have that it is raining, and I have that raining implies being wet, and I have that wet implies slippery. Okay, so the question is, can I apply the inference algorithm on this, modus ponens, using just modus ponens, and infer new rules? How does that work? Let's actually try this out using the system that we looked at in the overview lecture. So let's say it is raining. Okay. So it says I learned something. I can look at the knowledge base. So let's look at what is in the knowledge base. So raining is in the knowledge base. Okay. I can say if it is raining, then it is wet. Okay. So it says, oh, I learned something. Let's look at the knowledge base. So it is raining. It has raining implies wet. That is what this means, because rain implies wet is equivalent to not rain or wet. right? That's what implication, logical implication means. And then based on these two things, it actually derives wet. It applies modus ponens. Remember, I have rain. Rain implies wet. What does modus ponens give me? Modus ponens gives me wet. Okay? So I can derive wet. Let's add if it is wet, it is slippery. And let's see what that gives us. So it says I learned something. Let's look at the knowledge base. Okay, so we have a bunch of things, right? So these are things I added. I added rain. I added rain implies wet. I added wet implies slippery. From the first modus ponens that we applied, we got wet. We can apply modus ponens on wet, and wet implies slippery, and we can get slippery. So this slippery is added. We also get another formula here. Rain implies slippery. And modus ponens actually doesn't get us that, but this is using other types of inference rules, not just modus ponens. And if you apply other inference rules, you might actually get rain implies slippery here. Okay. All right. So let's look at this exact example here. All right. So rain and rain implies wet will get us wet, right? So we apply modus ponens again on wet, and wet implies slippery, and that gets us slippery. And if the only inference rule that we have here is modus ponens, then we have converged. Knowledge base is not changing anymore. We have derived wet and slippery. We have derived new formulas, but we have converged at this point, and we can't derive anything more. Okay, so we can't derive a set of other things here, right? Like we haven't derived like not wet. Probably a good thing that we haven't derived not wet, because not wet is actually contradictory to our knowledge base. Like it's actually not true, right? So we shouldn't be able to derive not wet. That's a good thing. In addition to that, we weren't able to derive rain implies slippery, which is actually true, right? Like if you think about entailment and what is the truth, right? Like rain implies slippery is entailed here, but we weren't able to get that by just applying modus ponens. And we will talk about that in general in a few slides, like why is it that we can't get rain implies slippery, and what can we do to make sure that we get everything that is entailed. Okay, and that is kind of like the same question as like we see here, right? Like what is the relationship between entailment and inferring and deriving? So derivation and entailment, how are they related? Are they the same thing, or are they doing different things? And does it depend on the inference rule? Okay. All right, so the Desiderata so far is we have semantics. Semantics is really about truth, right? It's about entailment, like about the meaning, like what is actually true. When we say a knowledge base entails F, what that means is that models of knowledge base is a subset of models of F, and in terms of like meaning, like that is actually what the truth is. On the other hand, we've talked about syntax. In syntax, we just do symbol manipulation, right, using inference rules. We've looked at modus ponens as an inference rule, and we have looked at things like derivation. So knowledge base derives F. Okay, so how are these two related? Let's talk about that. And that brings us to the idea of soundness and completeness. Okay, so we're going to talk about soundness and completeness. So let's look at this as an example. So imagine that you have a glass. Okay? And things that go inside of the glass are formulas. Okay? And imagine that anything that is inside of the glass is the truth. So what does that mean? That means that knowledge base entails those formulas. So every formula that is true is going to be inside of the glass. Okay? So the idea of soundness is that if I'm applying inference rules, if I'm running a bunch of inference rules, the formulas that are derived from those inference rules, I want to make sure that they're also going to be inside of the glass. I want to make sure that they're also true. Okay, so the idea of soundness is that a set of inference rules are sound if the formulas that are derived following that inference rule is going to be a subset of the truth, which is that the set of formulas that are entailed by the knowledge base. Okay, so they're going to be inside of the glass. They're going to be true. Maybe they don't fill the glass, that's fine. But what this is telling me is that anything that I'm deriving is still going to be true. I'm not going to derive something that's absolutely false. And that's a very important property that you want to have. In general, like you would want to have soundness. You want to have inference rules that are sound, because otherwise we would be deriving things that are absolutely false, and that inference rule is not useful. right? Like we want to be able to derive things that are at least true. Okay, so that is this idea of soundness. On the other hand, there's kind of like the other side of the story, which is about completeness. Completeness is about making sure that you're deriving everything that is true. Again, remember, everything that is inside of the glass is true. And the idea of completeness is that you got to make sure that the formulas that are entailed, the formulas that are inside of the glass, are going to be a subset of the formulas that are derived. So what that means is that your derivation rule makes sure that you are getting all the formulas that are true, or even more than that, right? Like if you talk about completeness without worrying about soundness, you might even be deriving things that are outside of this glass, but you want to make sure that you are deriving everything that is inside of the glass too. So everything that is entailed, and that's the idea of completeness. Okay. So if you put soundness and completeness together, you get a filled up glass, right? You get everything that is inside of the glass and just everything that's inside of the glass, okay? Which is like everything that is true, everything that is entailed, okay? So soundness and completeness is about the truth, the whole truth, and nothing but the truth, okay? So soundness gets you nothing but the truth, everything that's inside of the glass and nothing outside of the glass, because that would be bad, right? Like you don't want to get something false. That's what soundness gets you. Completeness gets you the whole truth. Make sure that you get everything that is inside of the glass, and like nowhere is like kept empty, right? Like you're deriving like all the formulas that are inside of the glass, and that is what completeness gets you. In general, you want both soundness and completeness. It would be awesome to get both soundness and completeness. And if you get both of them, then entailment and derivation are equivalent, right? Like if you derive something, you'll make sure that it's equivalent to the thing that you're entailing. In practice, soundness is more important, right? Because you don't want to derive something that is false, and maybe you don't get all of the truth, but maybe that is okay. So in practice, soundness, we prefer to get that first, and then push towards completeness. Okay. So going back to here, so soundness and completeness is the thing that connects these guys together. So soundness and completeness. Make sure that these two are equivalent. Maybe I should write that here too. Okay, so we talked about soundness and completeness as things that are relating in entailment and derivation. Okay. All right. So, and these are properties of inference rules. So the question is modus ponens sound, or is modus ponens complete? What can we say about modus ponens? Because that's the only inference rule we have seen so far. Okay. So remember modus ponens, right? Like we have rain, and rain implies wet, and modus ponens gets us wet. So is that sound? So how do we check soundness? So to check soundness, right? Soundness is about the meaning. It's about checking if it is actually like inside of the glass, right? Like the thing you're getting is actually entailed. So how are we checking that? We look at models of rain. Models of rain is this shaded area. We look at models of rain implies wet. That is this shaded area. We take the intersection of them, right? Because models of these two formulas is the intersection of these two models. That is the darker area. And the thing we're going to check is that if this darker area is going to be a subset of models of wet, is it going to be entailed, right? Like we're checking entailment because that is about the truth, right? Like that is the thing that checks the truth. So models of wet is here. And then, this darker area is actually a subset of models of wet. So it turns out that modus ponens is actually sound, right? Like we are inferring formulas that are actually true, okay? So it is sound. Let's look at a different inference rule. So I have a made up inference rule that says if you get wet and if you get rain implies wet, can you infer rain from that? Okay, so you've got wet and raining implies wet. Is it raining? That's the thing you're checking. So this inference rule, similarly, I can look at models of wet. I can look at models of wet implies, rain implies wet. This shaded area is going to be the intersection. And that is not a subset of models of rain, right? Like as you can see here, that's not a subset of models of rain. So what that means is we don't have entailment here, right? So because of that, this particular inference rule is actually not sound. So, All right, so the nice thing about modus ponens is it's actually sound. But the next question to ask is modus ponens complete? And I want you guys to remember this example that we looked at, right? Like we got a formula, we got rain implies slippery, and that wasn't from modus ponens, right? Like modus ponens wasn't able to get that. So this kind of gives us a hint that modus ponens is not complete. It's not going to get everything that is actually like entailed and is actually true. But yeah, let's look at an example. I'm not going to do justice in proving like that modus ponens is not complete. I'm mainly just going to look at a few examples. So yeah, so let's look at another example here. So let's say our knowledge base is rain, and if it is raining or snowing, it will be wet. Okay. So the question is if we can infer wet using our modus ponens rules. So first question is it actually true that it would be wet? Just like think about it like intuitively, think about it like logically, right? Like if you just think about it intuitively, you know it's raining. You know if it is raining or snowing, then it's going to be wet. So then it's got to be wet, right? It's raining, so it's got to be wet. So like if you just think about it intuitively, like you kind of like realize that wet got to be entailed here, right? Like wet, like from meaning perspective, right? Like wet should be included, or we should be able to like get wet and incorporate it in knowledge base. But modus ponens is not able to infer that. So why is it not able to infer that? Because in modus ponens, we have this very specific syntactic form of F and F implies G. And then this formula doesn't match that, right? Like it does have this or, and modus ponens doesn't really have ors in it. It doesn't really have any branchings in it. And because of that, like I can't really apply modus ponens here. So knowledge base here actually entails F. F is entailed. It is going to be wet. But syntactically, using just modus ponens, I'm not going to be able to derive F. And then based on this example, like you can kind of see that modus ponens is not complete. Like we're not able to derive everything. Okay. So one other thing I want to note here is modus ponens is kind of interesting. It's just looking at positive examples, right? Like you have a bunch of positive clauses, positive formulas, and based on those formulas, you're able to infer something positive, and again infer something positive, and infer something positive, right? It doesn't really have like these ors or negations, and that is why it's not able to infer this particular property, because we have an or here, because it's not able to capture that. And again, it's like applying things syntactically, so it doesn't care about meaning. So how can we fix this? So the question is, going back here, right? Like we just saw that modus ponens, sure, it's sound, that is great, but it wasn't complete. And ideally, I want to be able to get both soundness and completeness, because ideally, I want what I'm deriving would be equivalent to what I'm entailing. I want both of them. So a question that we're asking now is, how can we fix that? How can we fix the fact that modus ponens is not complete? Okay. And that's the topic of the next few modules. So we have two options to fix this completeness. First option is maybe we should restrict propositional formula. So propositional logic, maybe it is too large. If we restrict it, maybe we can restrict it to a specific set of propositional logic that only has these things that are called horn clauses. And under that scenario, if you're looking at propositional logic with only horn clauses, it turns out that modus ponens is both sound and complete. The other option is maybe I don't want to change my propositional logic. I want to keep all of propositional logic, but maybe I should be looking at more powerful inference rules. So modus ponens seems pretty simple. Maybe there are more powerful inference rules that I can use. And specifically, resolution is an inference rule that we are going to be talking about, which is both sound and complete. So next module, we'll be talking about horn clauses, propositional logic with horn clauses, and the fact that modus ponens is sound and complete. And then the module after that, we'll be talking about resolution and how we can use resolution and the fact that it is sound and complete.